Hello everyone, this is Mahdi. Nice to be with you in this work in progress track in the 39th ISTC. I'm going to turn off my video during this short presentation for a better focus on the contents. This work has been carried out by ADERSIM experts from York University, including myself. In this work, we've used a two-stage approach to simulate the spread of an infectious disease in a sample ICU. This presentation introduces a two-step approach towards a modeling problem. The first step uses agent-based modeling and discrete event simulation. And the second step can use a variety of modeling techniques, including system dynamics. Using system dynamics for the second stage would yield a nice way of integrating all three modeling techniques. However, this presentation does not contain a system dynamics model. It focuses on how the first stage simulation is implemented and how it integrates into the second one. Since system dynamics can be used in the second stage, we thought that this approach would be interesting for the system dynamics community. We want to learn how different intervention policies in populous physical environments would affect a breakout. We suggest a methodology that works for different social settings, such as schools, hospitals, places of worship, markets, etc. It helps determining the most effective strategies in terms of controlling an infectious disease, such as COVID-19. To model this problem, we need to know contact rates between the people, but that information is usually not readily available. There are several ways in which the contact rates are calculated or estimated, such as using RFIDs or other sensors in the people's clothing, using AI-supported technologies to analyze CCTV video footages, interviewing people about their daily contacts, and guesstimating the contact rates based on other available information. In this study, we suggest a fine-grained model that simulates the detailed movement of the human agents in the physical environment to calculate those risky contact rates. Detailed schedules of different agents as well as the workflows in which they are involved have been used to create this simulation model. You can see a video of such a simulation as I speak. The full version of this video is on the same YouTube channel from which you are watching this video. These moving circles are different agents from different agent groups or agent types that interact in this physical environment, each with their specifically assigned schedules and workflows. This is a fine-grained simulation that needs a lot of computational power and time to render. It is not very suitable for long-term simulations, as it can take a very long time to get the results for a set of suggested policy measures and different combinations of input parameter variations. However, it can provide the needed input parameters for a more abstract model that simulates the same environment in the long run. In other words, the aim of the first model is to generate input parameters, or the average contact rate per pair of agent type, as its output. During this fine-grained simulation, the system records risky contacts based on a predefined criteria in its most fine-grained level of granularity. Each instance of contact between a pair of agents is recorded separately. We then aggregate and normalize this data to make it useful for the second stage model. During this fine-grained simulation, the system records risky contacts based on a predefined criteria in its most fine-grained level of granularity. Each instance of contact between a pair of agents is recorded separately. We then aggregate and normalize this data to make it useful for the second stage model. For example, we can aggregate the individual contact data at the first dimension by removing the specific contact instances to get the average contacts between specific agents. Then we can aggregate it further on the second dimension to get the contacts between each agent and the specific agent types. We can go one level further and aggregate the data on its third dimension to calculate the normalized contact rates between different pairs of agent types. We have discussed the details of this process in a preprint manuscript, and the link is available on the descriptions of this video, along with a few more application examples. For model validation, we were in touch with the field experts throughout all the modeling stages. And we also cross-checked the outputs with some of the already known contact rates within similar and different environments. And the outputs were also within the expected ranges of a panel of experts. We believe that it's a good start, although it requires more efforts for validation, and external validity requires much more modeling in different physical settings that might require other considerations that are currently not thought of. If you have any questions, suggestions, or concerns, please be in touch through my email address listed here. Thank you for watching this video up to the end.